Anyway, so today we will have talk by Ivan Veselic, and he will talk about uncertainty principle and spectral analysis of Schroedinger openings.
Many thanks for the invitation and the opportunity to give a talk here. So, in some sense, this talk will be related to a talk I gave in the workshop which you mentioned. There I will be more talking about applications to random Schrödinger operators. And here I will expose more of the background, so there will be some overlap in the results, but the talks are kind of also independent. Okay? So this is also the reason for the rather general title. And I will start maybe with a kind of abstract setting. You have some region lambda, you have some function on the region lambda, and you have some subset, I will call it S. And knowing some information about the function on the subset, you would like to know as much as possible about this function on the total set. Well, sometimes this will not work. For example, if you have the characteristic function of the balls, then any prediction you do will be kind of not appropriate. So this tells you that you should complement this information which you have locally on these balls, right? Local information here, this has some local properties, with something else in order to be able to gain understanding of the function f as a whole. Okay? So what could this be? Well, you could think of regularity properties, that you say you are in a certain Sobolev space, you have a smooth function and so on. But of course you have also smooth functions which are thus supported in the gray set, so also this is a problem. So maybe rigidity is a better term for this. And you can already feel that somehow uncertainty principles are kind of coming into the game here. Well, and if you have both this local information and some global knowledge of the function, then you may be successful with your task.
What is rigidity?
Well, so now this is kind of vague terminology, and then later I will become more precise and present things which are called theorem and okay, so this is a general setting, and maybe you also saw that this subset S does not have just one component, but it has many components and they are kind of spread out. So I want to...
What has components?
You see this gray set has many components, many connected components. It's not one subset, one connected component. So this will also play a role in this purpose of obtaining knowledge of f on the whole of lambda.
So lambda is your square and S
Exactly.
is the union of degree.
Exactly. Yeah. But everything will become more precise later. So here just again conveying you a feeling of this geometric aspect which will play a role. Imagine that you are able to choose S. It's not a given a priori, but you have some kind of strategy of choosing S. And maybe a good choice would be, if you have a large set lambda, to choose some kind of periodic arrangements of subset, because then you will kind of explore all regions in space and get a representative picture of F. So a natural choice would be a periodic arrangement of balls, and this equidistributed set, which I will make precise later on precisely, could be seen as a generalization thereof. So something like this should be kind of a good way of doing it as well. This means that you will be also independent of some small perturbations. Anyway, you would like, if you think of the set lambda now to be an infinitely large cube, like RD, that it's relatively dense, so that you don't have arbitrary large holes in lambda without holes. And you can think of the lone set, and typically you would ask the subset S to have positive density. Okay. Now comes my favorite example. No, this is one example for the geometry. So if you have a Penrose tiling, then you have a graph. The graph has some vertices, and now you place in every vertex a ball. Okay. And then you put a lattice over it, and then you see that if you choose a box of a certain size, inside of each unit square you will find one of these balls. And if you choose a larger cube, it will still work, and so on. Okay. So this is an example of a non-periodic set where this condition is. Okay, and now we come to kind of a benchmark example where things like worked out beautifully, and this is the quite well-known sampling theorem by Nyquist and Shannon, which is used in telecommunications and signal processing. So what's the situation? You have a function which is continuous, which makes it possible to evaluate functions in points. You have an L2 function, which gives you a nice notion of a Fourier transform. That's written here. And now we assume that the Fourier transform is compactly supported. So in telecommunications, you speak of a band, what you're using, band of frequencies which you're using to construct your signal. Okay? And now somebody is transmitting this signal and you are recording it and you want to reconstruct what he's saying to you and say that it's important to know that it's enough to have a sample on a discrete set rather than on a continuum of values. Okay? And you see this is a lattice, and actually the lattice scales with the k. It's inversely proportional to the width of the bandwidth of the frequencies. Okay? And then you define this function at the point x in the following way. You take these samples where you evaluate your signal, and then you put a weight to it, which depends on the distance between x and the lattice sides. Okay? And then you get a new function. Well, and this sum, this infinite sum, actually converges absolutely uniformly, and this function is the original function. Okay? So just knowing the values on a discrete set, you recover the whole thing. That's not that surprising, because if you have a compactly supported Fourier transform, you have a holomorphic function, an entire function, and you have a discrete set accumulating at infinity a reconstructed function. So in complex function theory, kind of
in
tells you.
Fourier, it's the standard. This is the standard expansion.
Exactly.
If
So
you
it's,
think the expansion.
I mean, it's also equivalent to a lot of basic facts. You can show that it's equivalent to the Poisson summation formula. So I think this is the way how electrical engineers look at Fourier transforms. But of course, it's a kind of equivalent to many deep statements.
Would there be a similar thing in higher dimensions, Rn?
I'm not aware of such a result, and I will tell you in a second why it may be different. But before this, I want to point out something else. You see here you have a very strict condition that your function is supported on a compact interval, and you might have situations where you have some noise outside of this interval here, right? Where you don't want to have a strict condition. And also, if you have this strict condition, then this means that the function f is kind of, it doesn't have compact support, and you have to listen very long to the signal until you get information. So it could be interesting in looking at functions which are like Gaussians, so they are heavily concentrated in a finite region, but then have tails. And then there's this nice estimate for the aliasing error, which tells you how far off is this function from this function if this is violated. And you can estimate it in terms of the tails. Okay, so this is kind of the optimal situation you can dream of, but as far as I understand it, you cannot expect such things in higher dimension. Because if you say think of polynomials, then it's so if you have a finite degree polynomial in one dimension and you know that it vanishes at sufficiently many points, you know that the polynomial is zero. If you have a multivariate polynomial, it can vanish in a million points. It doesn't, even if you have just degree 100, it doesn't tell you anything. So the situations, to my understanding, is really different in higher dimensions.
But Poisson summation formula, wouldn't it work? I mean, just
This
would work, but I don't know whether this equivalence works in the higher dimensional setting as well. Right? So I cannot give you a total, and I haven't seen anything similar in high dimensions like this formula. Okay, but now I move on a little bit closer to Schroedinger operators, and I will present a result which is of interest if you want to study time-dependent Schroedinger operators or heat equation, and it's a kind of a spectral result. You look at a box of side length L. So this is, as before, we have a finite region in space, but eventually we will be interested in what happens if you choose L very large, or like a sequence of boxes which exhaust the spaces. Then you have this collection of balls of radius delta, and now I want this kind of very strong type of equidistribution. I say within each unit cell, within each periodicity cell, there should be one of these balls of radius delta, wherever. You can push it around, but there should be one of them. And then, well, I have this notation lambda L for this big box, and SL delta, this is the union of balls which you see inside of the window. Okay, it's an infinite collection of balls, but you look now at the finite size. Okay, and then you have the following statement. So if you fix delta, that's the radius of the ball, and K, this will tell you the size of the potential, then there exists a constant such that for any potential which has supreme norm bounded by K, and then for either Dirichlet or periodic self-adjoint version of this Schrödinger operator restricted to the box, and for any function real valued in the kernel, and from the domain, I mean, I did not write it explicitly, but I want it to be domain, you have this inequality which compares the norm, the L2 norm, on the whole box and on this collection of balls. Okay? So there's one inequality which is trivial. Of course, you have a non-negative integrand, so certainly this inequality holds. So this is larger than this here. And you want to complement it with the other inequality by paying a constant. Okay? Now, really, the interesting thing is to know on what this constant depends, on what it does not depend. So already how the theorem is formulated, it tells you the following. This constant does not change if you move around these balls as long as each ball stays in its own periodicity cell. Okay? It does not depend on the scale L. Okay, you can take, it's independent of the scale. Of course, if I choose a much larger window here, I will have also more balls inside. So the number of balls grows with the volume. Also, this constant depends on the potential only to the supernorm, so you don't need any kind of regularity, any kind of smoothness, derivatives, or whatever do not enter.
I'm sorry. What is psi?
Psi, this is a function in the kernel, so it's like an eigenfunction to the eigenvalue 0. It's in a kernel. Well, and the sorry, delta is the radius of the ball.
Okay.
And so the one more question you can ask is, what happens if I make the ball smaller? If delta becomes smaller and goes to 0, then I have less information locally, so what will happen to my prediction? And of course, the prediction will become worse. This means this constant will go to 0, and actually you can estimate it and show that it goes to 0 in a polynomial rate with some n, and I will elaborate on this n later, what it is. We'll do a formula for it.
And the size of this kind of cell lambda 1, is it fixed?
Well, it's size 1, but you can rescale everything.
But it's fixed.
It's fixed.
It doesn't matter 1 or 5, but it's a fixed.
It's fixed.
one.
It does not change. So what changes is this L, but the smaller scale remains fixed.
So even you also assume that psi then satisfies the boundary condition.
Exactly.
Right. Okay.
Yeah. So this is, I said it just by words, but if I say this, it means that this.
And you mean Dirichlet or any?
Dirichlet, periodic, Neumann.
What you said is any
So
any boundary condition?
So it's written here, Dirichlet or periodic
Oh,
boundary
sorry,
condition,
yeah,
and
sorry.
this thing, and Neumann would work as well. Okay, now of course, the eigenvalue 0 is nothing really special, right? If you have a general eigenvalue, you can push it around. The only thing what changes is now you have a different potential. You shifted your potential, so wherever you have a dependence on the potential, now you have a dependence on the eigenvalue as well, right?
Where E can be in a compact set.
Sorry?
Where E can be in a bounded set. So
Exactly, so you
just
get
stick
some
it-
uniform.
just stick it.
I mean, somehow what's important for the applications is to ask what happens if you don't have a pure state, but you have a mixed state. You have a linear combination of three eigenfunctions. What things change? Okay. So this you can write that psi is now the range, and now let's say you take a linear combination of eigenfunctions up to some energy cut of E, right? This is, you don't choose eigenfunctions with too high oscillations. And now I will formulate the full kind of question with all the terminology, but it's actually equivalent to this short thing which you see here. So you fix delta, you fix some constant which controls the potential, you fix the cutoff energy E, and you ask whether there's a constant such that for any measurable potential, bounded potential by K, all scales, all equidistributed sequences of balls, you have this inequality of quadratic forms. So why inequality of quadratic forms? So I write it in a different language now, but what you consider here is the multiplication operator with the characteristic function of the set of balls. This operator has large kernel, but it's not negative. And you are asking, if I restrict it to this subspace of eigenfunctions, okay, do I gain on this subset positive definiteness, right? Do I get on this subset an invertible operator, which is kind of characterized by this lower bound? Okay, and you see, here we take an infinite interval, but basically you can say it's a compact interval because we have a bounded potential, so you have no eigenvalues below minus k. It's basically a bounded, a compact interval from minus k up to e. Right? You can modify this slightly and put in an arbitrary interval a to b. Okay? It's just slight modification, slightly more general. You don't have just now e to play around with, but e and b. Right? And so Adolf Klein gave an answer to this. If the size of this interval, gamma, is small enough, depending on the model parameters. So it's something exponentially small in k, so it's like delta to the power k, something like this. So it's for very short intervals, but for many purposes this is good enough. For instance, if you're interested in continuity questions of the energy, integrated density of states, something like this, then you look for small intervals, you establish continuity there, and then it's a local quantity, a local property, so it makes sense. Nevertheless, there are other questions where it's important to have the full statement, where the interval ranges from minus infinity to e. Okay, and so we have this theorem, which reads as follows. There exists a constant, which depends on the space dimension, 1, 2, 3, wherever you are, and nothing else, such that for any positive delta, any non-negative energy, any scale L, actually it could be any positive real number, it doesn't even need to be from the integers, for any measurable bounded potential, and for all equidistributed sequences of balls, we have this inequality. So this is the same inequality you saw before, but now we have an explicit form of this constant, which gets small with delta, it gets small at polynomial rate, and we see on what it depends. It depends on this potential subnorm to the power 2/3. This is the same as in the two results before, and in the energy it's a little bit better behaved, so it's just square root of the energy. Okay. And you can write it also in a different way. You can say, if I pick a psi, which is from this subspace, then I can compare these two norms, right? This is the total norm, and this is the norm which I get after mapping it with these characteristic functions. And I have a double-sided estimate for the L2 norm, right? This is another.
Why you have square root and 2/3, which is
Okay, I will talk about this
strange from the
later.
point of view dimension.
So the conjecture would be that also in the potential you would have square root, but methods available today do not allow to do better. And this depends on the Kalman estimates. Maybe I hope I have time to discuss this later.
And you definitely cannot go better than square root. This is what you are saying.
I think square root is natural if you think of the scaling. Yes, I think that this is kind of the natural thing. This is the natural thing. I mean, you can in some sense say these functions in here, they behave like polynomials of degree square root of e. That's, I think, the natural intuition. And then if you start studying for such polynomials, how they vanish, this is the natural.
Even?
Yeah.
Is there a conjecture on the k naught? I mean, that it goes like e, that you have that. I mean, like the volume of the ball or something. Or
The k not here. This
yeah,
one.
the dependence on the dimension. Is there are conjectures.
No, I mean, I think in the K-naught we put all the rubbish. We did not even care about it. I mean, we did not go that far. You have already to work out to get this dependency. Okay, so I'll just
It's
rewrite
valid for dimension 1, 2, 3.
Any
on any dimension.
dimension.
Any dimension.
cannot
Okay, so I will write it now in a third way because I later want to discuss some things to this. So this is again the same result. This is the same picture. Big cube lambda L, this collection of boxes, Schroedinger operator with boundary conditions. You fix delta energy, then you have this, so that for any potential, taking values between the two, you can take now eigenfunctions, obeying this relation. You take arbitrary coefficients, you build this linear combination, and then you get this inequality with this thing. It's just the third formulation of the same thing. It's nothing else. Right? Of course, you know, this number k, how many eigenfunctions you have will increase if you enlarge lambda, right? The bigger lambda is the more eigenvalues you have, so it's always a finite combination, but as lambda grows, you
You mean some larger like L, right? Not lambda, but L.
L, yeah, L.
But the same.
What does the subscript UC, what does it stand for?
Sorry?
C
Unique
subscript.
continuation. This is the prominent player. Okay, so this is a theorem, and well, so I just want to briefly mention, as far as I know, some earlier results. Maybe I cannot discuss all of them in detail, but there are specific situations where you can, where these results are more accessible. So for example, if you have low energies, you take your quadratic form, you do partial integration, you see the gradient of the eigenfunction is bounded, is small. So this means this eigenfunction is rather flat, and if it's rather flat, then kind of all these things are very believable. Similar arguments and related arguments are valid if you're not close to the lowest spectral edge, but also close to internal spectral edges which arise, for example, in periodic Schrödinger operators. Also, if you're in a periodic setting, then the Bloch theory is very powerful, and you can derive results this way.
What is S? When you say B and SB is the potential?
V is the
and S-
potential, S is the set of balls. So if all the balls are arranged periodically, everything is periodic, and you can reduce basically things on the unit cell. You get rid of the scale L, and then you're on a unit cell, a fixed torus, and you're in a compact situation. And also in one space dimension, things are nicer because you have ODE techniques at disposal, rather than fighting with Kalman estimates. Okay, good. But this is just, this is not in some sense representative of the literature, because I'm just well acquainted with the stuff done in random Schrödinger operators, but then I saw that in other areas you have many results, maybe without potential and so on, but in a similar direction. So somehow in this business of random Schrödinger operators, some people call it scale-free unique continuation principle. It's a quantitative unique continuation principle. It's independent of the L, so let's call it scale-free. You see also an uncertainty relation in the background. You see this eigenvalue equation is a restriction in Fourier space, like in Shannon's theorem, which enforces flatness or delocalization in direct space. Or you can speak about gain of positive definiteness. This is what we discussed earlier with this quadratic form. And if you go into the literature about control theory for the wave equation, heat equation, or Schrödinger equation, then people call such things observability estimates. Or one of these things they also call spectral inequality, which is a very unuseful term, because you wouldn't be looking in Google for spectral inequality, right? Okay, and then there are two more relations which are kind of not that direct, but I would like to explore them. One of them is the relation to quantum ergodicity. So what's quantum ergodicity? Kind of very briefly and vaguely stated. If you have a certain classical system with a chaotic ergodic flow, then you quantize it, look at eigenfunctions, and you think that eigenfunctions with a high index should, if you look at the corresponding measure with this density, it should somehow be close to the uniform distribution. Okay. The same thing is in so-called compressed sensing and sparse recovery, so-called uniform uncertainty principles and restricted isometry properties. These are two names for the same plane control. And this I want kind of to elaborate. So about quantum ergodicity. This is restricted to certain systems. If you think of manifolds, it would be kind of manifolds with negative curvature or something like this, where you expect ergodicity. But I would like to apply it in a more general setting. I mean, basically we had something like the torus before, flat torus. So I would like that it depends too much on the classical behavior, then of course you cannot expect so much. So I'm looking at some kind of more uniform but weaker analogs of quantum ergodicity, okay? Which do not depend on the fact that you're actually ergodic or periodic or whatever. So the kind of most non-ergodic situation is maybe if you consider sphere, right? This is a very integrable situation. And let's see what people expect there. Well, there the eigenfunctions of the Laplacian unknown. These are spherical harmonics. And if you go up with the index, there are some of them which have kind of a rather singular behavior. They concentrate very strongly at the equator and have exponentially little mass near the poles. So in general, you cannot hope that this will work. But then people have looked at this. If I choose now a different sequence of eigenfunctions, maybe it will work there. So there's this conjecture about certain linear combinations of the spherical harmonics, which are at the same time eigenvectors of certain Hecker operators, which I will not formulate here. So if you choose this special sequence, there is this conjecture that they will converge to the uniform distribution as you go along the sequence to infinity in the sense of integration against continuous functions. And there's a partial proof, moments 1, 2, and 3. 1 and 2 are trivial, and 3 is the hard part, which these guys proved. But they didn't get further. However, if you...
The two-dimensional sphere, the sum is radial, no? The sum of
the sum... So you fix your energy, and then you take the sum.
Yes. Sum over m, is that radial? Yeah.
I cannot answer you. I don't know whether I understand it correctly, and I'm not sure whether I can answer.
Take the sum from m equals minus L to plus L from the y L m. This is not
Combinations, it's not exactly.
Yes, it's a linear combination.
Und just what we
One
just
has
saw.
conjecture that there exists a sequence of linear combinations.
Yes, so
But
my
you have-
question is it this?
But you just basically somehow, do you sum up all up to the energy E, or just
No,
for the
just
energy?
fix L, sum over m. No.
Some in one
This
energy.
would be
then.
trivial, right?
Yes.
Okay, I'm
I'm
not sure about
completely
this.
sure. I have
Yeah,
to verify.
maybe we can check this later. I mean, of course, you gain some symmetry if you kind of.
I think it was the project on.
Okay, maybe we can.
What is the sense of this eigenforms?
Okay, I cannot write this down, but these are certain operators which commute with the Laplacian, and then you say I will choose now a special basis which is simultaneously eigenfunctions of the Laplacian plus three other operators. Okay, but I cannot write it down, and actually it's motivated from studying certain negatively curved manifolds where they arise very naturally, and they wanted to transfer this to spheres.
Maybe I have done the same notation. Your m here, YLM, m is between minus L and plus L.
Exactly. Okay, but there exists a random version of this, where this is true. This is shown by Veselic. And basically, well, what we have already discussed, you have this high degeneracy of eigenvectors. And you can just say, for each fixed energy, I have a finite dimensional set of eigenvectors. I have unitary transformations of them, so I have a group acting of them. You take the Haar measure. So this is kind of randomness on the subspace. And then you take the product of the Haar measures, which gives you a notion of randomness for each basis of eigenvectors, right? Or orthonormal basis. So for a randomly chosen orthonormal basis, of eigenfunctions, with probability 1, you have this statement. So f bar is for a function defined on the sphere just the average. And here you integrate this function f against the density produced by the jth eigenfunction. And then you sum this up to energy E. You normalize by the number of eigenvalues we have, which you have seen up to energy E. Right? This is kind of a normalization, like an abelian Cesaro evenness. And then this converges to 0. Okay. Of course, there are some now relations and differences to the things which we have seen before. Here you choose a special sequence of linear or a linear combination of eigenfunctions, and then you actually get really close to the uniform distribution. So this constant which we saw before is something close to 1. It's not something like small or big, it's really close to 1. Whereas here, you choose an arbitrary linear combination of eigenfunctions. So in some sense, you have to cover the worst case scenario as well, right? You have kind of good linear combinations and bad linear combinations. And this kind of works for good ones, and this works for bad ones. And if you would like kind of to find an intermediate scenario, then you could start looking at such things where you choose these coefficients alpha k randomly, right? And then you create a random linear combination, and then you ask whether this relation, which we saw before, will be now true with a much better constant with a very high probability converging to 1 as you go up in energy. I mean, I'm not saying that this is important. I just want to kind of give a picture of an intermediate statement to illustrate the relation.
When you say choose randomly, what do you mean?
I'm not specific about this.
Just vague.
Vague, exactly. So I just want to show that
Okay.
there could be a relation.
But don't you have such a result already with the delta to the k0? Isn't your result, the CUC which you have here, should be bigger than delta to this exponent? But your concrete result, isn't this already?
Well, so I'm asking whether you can do much better than this. So is it possible to get something like much closer to 1?
With,
Right.
this, with the constant CUC?
If you introduce more randomness. Okay, so this was one of these excursions. Now I want to make an excursion into this sparse recovery and compressed sensing. So this is, in some sense, you can look at it as certain improvements of the discrete analog of Shannon's sampling theory. As before, I will continue to denote the Fourier transform of a vector with a hat, but now we have finite vectors. These are not infinite functions, but we are in a finite dimensional vector space. Okay, so there's this remarkable theorem by Candes, Rumberg, and Tau. You choose a prime number, you look at a cyclic group with m elements, and you have subset omega. This is an observability set. This is where you gather data. Okay? And then you assume that if you take the Fourier transform and you count the number of non-zeros times 2, that this is less than the number of your observations. Okay? So you're observing more than there are Fourier coefficients. Then the vector x is uniquely determined by what you see on the subset. Okay? And this is completely independent on the size of m. M could be 1 billion, I mean not exactly because 1 billion is not a prime, but kind of the next prime after 1 billion. Okay. If m is not prime, the statement is not true. Because you have subgroups and then you lose some injectivity and the proof breaks down.
What is that term?
This is the cyclic group. What you typically write is
Cyclic group.
0, 1, 2, 3 up to n minus 1, and you have an additive structure. You calculate modulo n. Okay, it's an additive group. And to define Fourier transforms, I need an additive structure.
But if m is not prime, could I get something like this with some restrictions on omega? I mean, omega not lying on a subgroup or whatever.
I will say some more soon, but
Okay.
there are like dozens, if not hundreds, of papers related to this question. And I will this will be just a glimpse in this whole thing. So moreover, it's not only that you have a uniqueness, but actually you can reconstruct the true x algorithmically by solving this program. You take all vectors which are consistent with your data, you observe something, and of course you want to fill up what you observe on the Fourier on your side. And then you look that on the Fourier side, the number of non-zero coefficients is minimal. So you get a vector, and this is the true vector. Okay.
Do you also require that the support is no, it's just
Yeah, this is just you continue with the same assumption. So you
okay.
have to. However, the problem here is this is a combinatorial program, so you cannot solve it efficiently. It has exponential complexity. Okay. So you want to replace it by a nicer program, like a convex minimization program, and instead of P0, consider P1. And basically, you replace the L0 norm, which is not a norm, by the L1 norm, which is a norm and is convex. L0 norm means just counting the number of non-zero numbers. Okay, so it's the closest thing you have with convexity. So the choice is simple.
But why is it computationally more feasible? It doesn't take as long to calculate the norms and to calculate.
Yeah. I mean, if you have a convex optimization problem, it's something totally different than a non-convex one. And I mean, and specialists tell you, so you can even rewrite this as a linear program. So it's really efficient. Okay, and the question is now, in the air, are P0 and P1 equivalent? Maybe under some additional assumptions. And here is the theorem. So what they do now is, they don't fix the observation set, but they do something what you suggested. They are very clever, and they just pick it randomly. Okay? So PS is the uniform distribution over all subsets omega of size S inside of Zn. Okay? You pick your observations at random.
Zn is Z factor.
Exactly, this thing we have been discussing, this finite group, finite cyclic group.
Z factor.
Z factor. Z factor and Z. Okay, so now we fixed three numbers, but for the moment we just look at M and S, forget about A. Then, if you have a vector with M components, and if the number of Fourier coefficients non-zero is bounded by S divided by log M, okay, M is a big number, S is not such a big number, then with very high probability the solution of P1 is unique and gives you the right result. Okay? Now, and if you want to specify how close you are to 1, then this A enters, you fix A, then you get a constancy A, and then if you satisfy this condition, you have polynomial convergence with the power A. So this is a little bit in the direction of what you
So it's P1, can you remember?
Sorry?
What is P1? Minimize of P1. What is P1?
P1 was this convex. You see, we have these two programs, convex and non-convex, and we are asking when is the solution the same? Different programs, but maybe same solution. And with high probability, it is the same solution under these conditions. Okay. Again, this has some relations to uncertainty principle. So you have a certain type of discrete uncertainty principle, which tells you if you have such a vector, and you add the number of non-zero Fourier coefficients and the non-zero coefficients of x, it's at least 2 times square root of m. And if you are willing to sacrifice a little bit of probability, then you can improve this. You should think of the square root of m as m divided by square root of m, and here you have m divided by log m. Okay, that's the case. Okay, and now we move on to something else. For the moment, Fourier transform will disappear, and we will be solving an inverse problem. Okay, an inverse problem with the linear operator b. Well, and all this theory works under this definition, which these three guys have introduced. So you have 3 dimensions. You have a rectangular matrix, so typically m is much larger than n. Okay. So you reduce dimension by applying b. And you look at the following inequality. You see, you have here some number delta s. If delta s would be equal to 0, then you would have something like an isometry. Now you sacrifice 2 things. You move away from 1, so it's just an approximate isometry. And the second thing is, you don't require this for all vectors y. I mean, after all, you are going from some space like with dimension 1,000,000 to a space with dimension 1,000. So you can hope for this. But you see, this should be only satisfied if m is such that the support, the number of non-zero coefficients, is bounded by s. So drawing is a little bit difficult in high-dimensional spaces, but basically if you are in R2 and you choose S equals to 1, then you just look at vectors which are in the union of the coordinate axis, right?
Is it a generalization
What is
of this
so-
discrete Fourier transform beforehand? Because the discrete Fourier transform.
As I said, for the moment, the Fourier transform just disappears from the stage. It will come back later.
What is support of y?
You have a vector and you count the number of non-zero
So
coefficients.
the number. Okay.
Yeah.
The cardinality.
Yeah, cardinality. Yes, sorry, I forgot here the cardinality sign. Yeah. Okay, and now we have a similar result as before. Imagine that you have a B with these numbers
And
here.
B is just a mapping.
Mapping, a linear mapping.
Linear.
Oh, I forgot to say linear. It's a linear mapping. Sorry. And you assume that this is actually positive. Otherwise, it's ridiculous to try to reconstruct things. It's no meaning in this. And then you pick an x such that the number of coefficients which are different from 0 is bounded by s. Okay, this is your a priori information. And then you want to solve this equation. Okay, but you see f has much less coefficients than x, right? So this is the non-trivial part. Well, but if this is satisfied with this constant here, then actually the unique minimizer of this problem, so what you do, you look at all vectors y which give you the correct observation data, and then you minimize among all these y's you look for the one which has the least number of non-zero coefficients. And that's the solution. This gives you the correct x. Okay. Actually, for this lemma, you just need this lower inequality, not the upper one. Okay. But again, as before, this is a very expensive program. It's non-convex. It says exponential complexity. And again, you can ask, can I replace it by something simpler, more efficient? Okay, and they have the following statement. You have again 3 dimensions: a big space, a small space in which you map, and a certain number of which determines your sparsity. This is the S. Okay. So you look at a linear mapping, and you assume that the restricted isometry property is satisfied with this condition. Okay. You have here these deltas. And you have to enlarge S to 3S and 4S, and then still this delta should be small enough such that this is satisfied. So this is a quantitative type of this. Now you assume that you have a vector x which is sparse, so the number of non-zero coefficients is bounded by S, and you have a certain error vector whose norm is bounded by epsilon. And then you have some observations which are distorted by noise. Okay. And then you look at the solution psi of the convex optimization problem, which consists of all the vectors y such that the outcome is consistent with your observation up to the error level epsilon. You have an error level epsilon, you cannot beat it, so you have to be satisfied with this error.
Do you also require that y is sparse in this?
You see, I require this, so this is a sparsity assumption.
For x, but down there in P2,
No.
y?
No.
Why not?
Well, you see, I minimize the L1 norm,
Yeah.
and the L1 norm is close to the L0 norm. So kind of I enforce the sparsity by this minimization. I favor sparse vectors over non-sparse vectors. Okay, so you get this solution. Of course, because of this error level, you cannot get the exact thing back, but the distance to the original x is bounded proportionally in epsilon. So that's the best rate you can hope for, linearly in epsilon. And you have a constant which just depends on this thing coming up from this uniform uncertainty principle. Okay. So really this uniform uncertainty principle captures how good you can solve this equation, although it's in some sense ill-posed if you want. Okay, and then they give also some numerical values that they tell you that this is not 10 to the power to the 10 to the 10 to the 10. Okay, it's something really fine. Okay, and then you can ask a further question. What happens if I loosen up this condition that I have sparsity, if I have some little noise, as we discussed it with the Shannon theorem? If you relax the compact support to having tails which go fast to infinity. Okay. To formulate this, it's good to look at the following notion. If you have a vector in Rm or Cm, and you have a number s which is smaller than m, then you denote by xs the vector which you obtain by deleting all the small values, the ones which are close to 0, and keeping the s biggest ones in absolute value. Okay, this is just a repetition. So they have the following theorem, which is the same as before, basically. The only thing what you relax is you do not require now the original vector x to be sparse. So you don't require that there are only s coefficients which are different from 0. Okay, so less restrictions, and of course your theorem has to change to account for this. How does it change? Well, you still solve this problem. You get a solution or minimizer of this problem. This is this psi, and the distance to the original x is bounded by the same term which we had before, plus an additional term. And this term depends on how well xs approximates s. So if x already had only s coefficients, which are non-zero, then this distance is 0, no additional term. Well, and if you have a very fast decay of the tail, then this will be very small. So you only need kind of approximate sparsity to solve this. Okay, and these two coefficients again only depend in this restricted isometry constant delta 4s. Okay, so these are some results where you have this, just to flash it back, where this restricted isometry property plays a role. But of course there's one big question in the air, and this is how to get such matrices, right? Maybe there is no such matrix B which satisfies this, or only small ones. So we have to discuss this once more. So this is just the repetition of the definition. And there are several constructions to get these ones, matrices, but they are all random. There are no deterministic constructions. I mean, you can do it, but then the relations between m, n, and s are not very good. So you don't reduce really the dimension very strongly. Now some examples. So one of them is the Gaussian ensemble. You take B with IID Gaussian entries, zero mean, and variance 1 over n. This is a random matrix. And I don't want to be very precise, but with probability very close to 1 for high dimensions, the uniform uncertainty principle holds if this condition is satisfied. You see, S is the sparsity. This is the number of non-zero coefficients you allow. Okay? And this shouldn't be too big compared with the number of observations. N is the number of observations, kind of less non-zero coefficients than observations. This is the general idea. And in addition, you have to pay this factor, which depends on the large dimension m, but this is small because it's logarithmic. Instead of this, you can also consider binary entries, plus minus square root of n with 1/2 probability. And the next Fourier ensemble, so this is another class, will be nice to connect back to the things which we discussed earlier. So here the procedure is the following. You take a square matrix, discrete Fourier matrix, and now this is not rectangular, it's square, so you delete a lot of rows and you keep just n of them. So you get a rectangular matrix. Now you normalize each column. Because of deletion, the columns are no longer normalized, so you have to normalize again. So you have now a rectangular matrix, and then this is a good matrix with high probability if this condition is satisfied. Okay? And this is something close to what we considered before, if you remember, because we were talking about conditions on the vector x and its Fourier transform, and you had something like few Fourier coefficients, and then you observe in direct space. So this is really a translation of this thing.
So you say randomly here, is that we understood as arbitrarily?
I think randomly, you see.
Select n rows randomly?
So when you select it,
some measure?
you take uniform distribution on all subsets of size n among them M. This is its uniform distribution.
Okay, then you say it's probability close to 1.
Okay, and then you can generalize this. Instead of taking the discrete Fourier transform, you can take any orthonormal matrix and do a similar procedure. Of course, you have to be a little bit skeptical because you see the identity matrix is orthonormal as well. Now, if you take an identity matrix and you delete a lot of rows, you get a lot of zeros, and you can no longer normalize your columns because there will be columns with existing just of zeros. So this definition should somehow capture this. Okay. So here, if U is an orthonormal matrix, select n rows randomly, so by uniform sampling, normalize each column in this rectangular matrix, and then you obtain B. Then the uniform uncertainty principle holds with probability very close to 1 if this is satisfied. And now what's new? This is this factor here. Okay, let's try to understand this factor. This script n is the maximal entry in modulus of your matrix. So in this case, with the discrete Fourier transform, it's just the square root of m. So you have square root of m squared, 1 over square root of m, squared. So this just cancels out. Okay. And if you have the identity matrix, this is 1. So you get here 1 over m. So basically this number is smaller than 1. So you have to choose s smaller than 1. So it's
So the maximum is over indices j and k, and u is ij, so what are k's?
sorry, it's a typo. K is I.
So all you just optimize the module.
Okay. Well. So now I think I have to be quick and kind of go back to continuum space again. So there's the connecting part is that in several statements which we have seen, you have an operator. Okay, I don't know what happened now. Okay, this happens automatically. You have an operator which is highly singular. Well, it has a large kernel, but then you can derive something like this with a certain constant here. And this constant is controlled. Okay, for psi out of some union of out of some proper subspace. Okay. And this thing we have seen in this discussion which was here, and actually in the case of the scale-free unique continuation theorem, it was a statement exactly like this. It's just a matter how you choose these subspaces. Okay, that's a little bit. So maybe I have just time to. Maybe I can have time to formulate a conjecture. So it's nice maybe to find some analogs of this uniform uncertainty principle in continuum space, where you replace vectors by functions. And there have been already some attempts and suggestions, and there are different versions, because in infinitely dimensional spaces we have a lot of ways to go to. And one thing which I put forward is the following thing. So if you fix two positive numbers, gamma and a, and you have a measurable set S of R, this should be something like equidistributed, in the sense that if you take any interval I, intersect S with I, and I has length A, then this measure is at least gamma times A. So you have density gamma on the scale A. Okay. And then you choose intervals, JK, S of them, all of length B, and you take the union. And then you take the spectral projection of the Laplacian on the interval from 0 to L, and you sandwich the multiplication operator with the characteristic function of this set S on the interval. Then you should get this here, which depends only on gamma, A, B, S, L, and not how they are placed. Okay, so this is something like this inequality of quadratic forms which we saw before, but the thing is here that this constant depends on S and it depends on the length B, but not on how they are related, how they are positioned. So you could take two energy intervals and shift one up, one down, and this shifting should not change the constant. Okay, I think I'm already over time, and maybe it's time to thank you for your patience.
Over time, I think you still have 5 minutes Right. Is Nazarov Fedor Nazarov or
Um,
Fyodor?
Fyodor, yes, yes.
Okay. Thank you. Other questions? Yeah.
This inequality too, how does it relate to what you already showed the result with the uniform continuation? What did you prove of?
Yeah, okay, so the thing is the following. There we take the interval from 0 to infinity, sorry, from minus infinity to e. And here we would take maybe intervals, like this would be E1 till, call it F1, then we have J2, I don't know, I can say E1 plus B. You see, they all have length B, I said. So you have E2 till E2 plus B, okay, and you have S of them, okay, and then you take the union of them. J is the union of JK. So this here, of course, looks differently than this, and therefore you expect different dependencies. Here you just want to know how it depends on E, on the cutoff energy. And here it should depend on the number of intervals and of the length of the intervals. But the question, this would mean, just take this situation, okay? You have two intervals, and in the Fourier side, you can ask, if I have here this interval, and if I have here this interval, and I just take functions which are from the range union of these two intervals, so E1 till E1 plus B, with E2 plus B. Okay, this is your restriction. And now you want to derive your unique continuation results. And you ask yourself, can you achieve this, that it's uniform if you push this interval to plus infinity?
Already for one goal, if you would have only J1, it's already
Yeah,
still
it's also, yeah, exactly.
So you're saying your constant does not depend on all your EKs?
Exactly. It depends on the B and it depends on the number.
Yes?
Yeah, so since you also showed some discrete results there, do you actually see some path of maybe getting some similar statements for boxes in CD, which one eventually would help one to attack the Bernoulli-Anderson problem?
Okay,
So-
certainly you don't have Kalaman estimates there, and I wanted to I wanted to say something about this in the second talk in the workshop, but I think I okay, say something now. So there's this classical result that if you have a function psi which is harmonic and which is identically equal to 0 here, and here you don't know what it is, well then it's actually everywhere zero, you can extend it. Now look at this ZD case. ZD, okay? Imagine you have here, how do we draw it? Maybe something like this. Okay, these are your lattice sides. And now this is the discrete Laplacian. And you know that your function is here identical to 0. Well, then it's here also identical to 0. So you have exactly the same result. But if you do the following, because you just solve equations, you know, you have just to solve an equation involving a few coefficients, this one, this one, this one, this one, and you have a recursion. But now you consider the following thing. And you know that your function is now equal to 0 on this side. Then you can have here everything equal to 0, then on this diagonal you put 1, on this diagonal you put 2, on the next you put 4, and you get a solution. And of course, you really would like to have something like that. You just know that it's 0 on a ball, on a convex set, so you just lose this kind of arguing. And it's kind of strange because in the continuum case you have rotational invariance and so on, and these properties you don't have in the discrete setting.
Other questions? Okay, let us thank the speaker.